Okay, into the third subtopic of the light and atoms topic, and that is the structure of the atom. And this topic will probably more have to do with light than actually with the structure of the atom, but those two things are inherently related, and hopefully as we go through this subject you will develop an appreciation of how inherently related light is to the structure of the atom. Let's get into it by looking at black body and emission spectrum. Okay, so what do we need to know? We have our learning intention from the SACE board here and our SACE criteria. So after this slide, hopefully you can describe the changes in the spectrum of a filament globe as the temperature of the filament increases. So firstly, let's talk about these continuous or black body spectrums. A solid, liquid or dense gaseous objects radiate a continuous spectrum. Continuous spectrums means it's a spectrum containing a wide range of colours, wavelengths, frequencies. We use these three words interchangeably. Each colour corresponds to a wavelength, and the wavelength is directly related to the frequency by the equation C equals F lambda, where C is the speed of light. And generally when we think of a continuous spectrum, we think of the continuous spectrum of visible light, which basically looks like the rainbow. You've seen that if you've looked through a spectrometer at the sunlight or something like that, you'll see all those colours there in the spectrum of the light. You also, I guess, see that when you get a rainbow, because basically the effect of a rainbow is water particles in the atmosphere causing all of the different wavelengths to bend at different angles, forming that rainbow effect. So think of that sort of rainbow, you're thinking about a continuous spectrum. Now, this continuous spectrum, though, doesn't just have to be in the visible region. It can go up into this higher energy end, which is the ultraviolet, or it can go into the lower energy end, which is the infrared region. So this process by which basically solid, liquid or dense gaseous objects radiate a continuous range of frequencies is known as incandescent. And you might have heard the term incandescent light bulbs, which are sort of the old style light bulbs that had like a wire filament in them, and you applied a voltage across it. That wire filament got really hot. It got so hot that it glowed and released light. Now, the frequency distribution, and hence the dominance colour, depends on the temperature of the object. So we'll talk about that in a sec. But maybe if we go back one step, when we talked about electromagnetic radiation, we talked about the idea that any accelerating charge or oscillating charge will produce an electromagnetic wave. So in this case here, you have atoms, whether they're in a solid, liquid or dense gas, and these atoms are made up of protons and electrons, which are charged particles. These charged particles, as they get hot, vibrate faster and faster and faster. As they vibrate faster and faster and faster, they're basically accelerating. So these charged accelerating particles will emit electromagnetic radiation, and we will see that electromagnetic radiation as, in a lot of cases, as light, as we've shown here. So let's get back to the real purpose of this. What is the effect here of temperature? Well, if we start here at a lower temperature, so we're down here, a low temperature may be typical of in an incandescent light bulb, particularly one may be working at a lower voltage. And what we would see is that will emit a spectrum shown by this red line. So this here is telling us the intensity on the y-axis. This is telling us the wavelength. Obviously, as the wavelength gets shorter, the frequency gets higher, and basically the energy gets higher. So this is releasing mostly very low energy electromagnetic radiation, and the high end of that is just touching into the visible part of the spectrum, so most of it is in the red-orange end. So this light at low temperature will appear like red or orange in colour. I'd say red, but it's shown orange here in this little graphic. This graphic comes from FAIR, so you can go to this link if you want and play around with this simulation if you like. Now, as you increase the temperature, so we get up to a temperature near what our sun is, you'll see that we get more lower wavelength radiation released, or more higher energy wavelengths released. And now we're getting all of the colours of the spectrum, all the colours of the visible spectrum are being released. When you add together light of all different colours, you'll get white light. So this will appear as a quite white light as shown here. If you keep heating this up, and you may have seen this, for example, with a blue flame on a Bunsen burner, or if you ever heat something up really hot, it'll start off going red and then eventually it'll go white hot. And if you keep heating it, it'll actually go blue hot. And that is because all the particles are vibrating so fast that they are releasing very high energy electromagnetic radiation. And the peak of that is actually into the UV, the part that our eyes can't detect but causes us to get sunburn. And we just see, we can only pick up the tail down here. This tail is dominated by the violet blue end and into a little bit the yellow and green. And so an object like this will glow a blue colour. So another way to look at this, if we look at this in terms of wavelength, we took it in terms of frequency, which is inversely proportional to wavelength. So here, as we go across the frequency increases, that also means as we go this way, in a sense, the energy increases, because E equals HF. We'll come back to that later on, but we've talked about that with photons. What we would see is at low temperatures, we will get something that would look more red in colour with the lower frequencies dominating. As we go into the intermediate temperatures, we will get all colours of the spectrum released, so it'll appear white. I can't really draw white, so I've drawn it as yellow. And then finally, as it gets much hotter, we will see the blue released. So T3, the temperature here would be higher than T2, which would be higher than T1. So that is the continuous spectrum and what I would call black body radiation. So in the last slide, we were really focused on solids, liquids, or very high density gases like within the sun. What we are going to look at now is where we have a vapor or a low density gas. And what we're going to do is we're going to excite that gas. Now, the easiest way to excite that gas is just to heat it up, so make the particles vibrate faster. But we can also heat that gas using an electrical discharge. You may have seen in the lab the discharge tubes, which we've used the whole voltage supply to excite the gas to emit light. You can also bombard the gas with electrons, and that would excite them as well. But generally heating or an electrical discharge is the way that we would excite those atoms. Now, what happens here is when we heat up a gas, we do not see a continuous spectrum with all the colours of the rainbow. We see what is called a line emission spectrum. So the first thing we need to be able to do is describe the general characteristics of the line emission spectrum of elements. The line emission spectrum consists of discrete narrow coloured lines like this on a dark background. So it's almost like those areas of negligible reinforcement in a transmission grating or something like that. So this is basically what an emission spectrum looks like, as opposed to a continuous spectrum which contains the full range of colours. We've looked at those through the spectroscope as well. Now, each atom, or probably better there should say each element, emits a unique line emission spectrum and releases light of unique colour or frequency or wavelength. Again, we can use them interchangeably. They all essentially represent the same thing. So the pattern produced can be used to identify elements like a fingerprint. So if you take a different element, then this will release a different set of frequencies, but that will be that range of frequencies will be unique for each element. So we can actually look at distant stars, we can look at what colours are being emitted in their emission spectrum, and that can actually help us determine what elements might be present in that star. So quite a powerful technique for analysing unknown substances is emission spectrum. For those of you who do chemistry, we also use this to identify elements in samples in chemistry, and we then further apply this to atomic absorption spectroscopy. We will talk briefly about absorption spectroscopy also in the next flipped lesson. So I'm going to go more into this in the next slide, but I just at this point want to just sort of start to make this link. The presence of discrete frequencies in the spectrum of atoms, like this, or elements, maybe I better should say, is evidence for the existence of discrete energy levels in atoms. So the way that they worked out that each atom has these discrete energy levels, and we'll talk more about those in the next slide, was because each atom released a unique set of frequencies. And we know from the photons topic that E equals HF, so there's a direct relationship between the energy and the frequency of a photon, and the frequency is directly related to the wavelength, and the wavelength is directly related to the colour. So, therefore, a unique frequency indicates a unique energy. More on that in the next slide. Now, I just want to quickly go back to something from the previous subtopic on X-rays. The characteristic peaks observed in the X-ray spectrum are due to emissions associated with energy level gaps in the target atom. So if you remember briefly when we did the X-ray spectrum, we drew something like that, and we had those high intensity peaks near the top, like that. So they were actually associated with these energy levels within the target atom, and it being basically more likely to release photons that corresponded to those energy level gaps. We don't need any more detail than that, but it's basically, the reason for those high intensity peaks is because of the energy levels in the target atom. So let's get into this in a little bit more detail. So the first thing we need to do, and I already started doing in this on the previous slide, is explain how the presence, oops, that wasn't a pointer. Let's go to a laser pointer, is explain how the presence of discrete frequencies in the line emission spectrum provides evidence for the existence of states with discrete energies in the atom. I already started talking about this before. Let's just go back to maybe what you learned in middle school science, and if you've done chemistry, you've done lots of this sort of stuff. And if we think about the atom, and let's say take an atom like neon, and then we would say, oh, neon has got 2 electrons in its first shell. Then it would have, it's element number 10, so it would have 8 electrons in its second shell. And then, so we would have talked about that idea of a 2-8 if we went on and did some chemistry, and it doesn't matter if you haven't in year 11 and year 12 chemistry, you would have learnt that those shells have subshells in them. So we'd talk about something like 1s2, 2s2, so that's the S subshell in the first shell, the S subshell in the second shell, and then 2p6. And we could go on, you know, we could get the third shell that oops, that's the wrong pen. We could get the third shell that comes after that, that could start to fill up if it needed to. So, yeah, we can have this picture in our mind of electrons all spinning around a nucleus, and basically, rather than really representing orbits as we sort of draw them in chemistry, these more represent energy levels. And in a sense, what happens is when we apply electrical discharge, or when we heat up that gas, what basically happens is it causes an electron to jump up into a higher shell, because that energy gives it some energy. That energy can jump up into a higher shell. And then what happens after that electron jumps up, we'll do a different colour here, electron comes up here, then it relaxes and it goes back. And when it relaxes, it releases a photon of light. So the light that we see in an emission spectrum is basically due to those transitions of electrons jumping up into higher orbitals and then falling down and releasing energy that corresponds to that gap. Now, that's how we look at it in chemistry. However, in physics, we more look at it like this diagram here. So we still have this concept of energy levels, and these energy levels still loosely correspond to these shells of electrons. But what happens is we have the atom, and we call what it's in its ground state or its ground level. And when we put energy into it, it will cause an electron to jump up into a higher energy level. Once it goes into that high energy level, it will then relax, and as it relaxes, it will release a photon of light. Now, very important point. These energy levels are like the rungs on a ladder. If you're walking up a ladder, you can either only stand on the bottom rung or the next rung up or the next rung. You can't have your feet halfway between a rung. It's just not possible. And the similar thing happens with electrons in energy levels. So if we excite this atom up here, this atom here, and this one here represents hydrogen, what we will do is when we excite it, we will put it up into a higher energy state. It goes up to there. So it can only jump up into that state. It can't go to an energy level somewhere between that state. And then when it relaxes, it will basically relax and it will release a photon that corresponds to that energy level gap between that electron, that level there, and that level there. So 13.6 minus 3.39. So it would be about 10.21, I think, from the top of my head. Electron volts. That would be the energy of the photon that was released. We could convert that energy into joules, and then we could convert that into a frequency, and then we could convert that frequency into a wavelength. So yeah, atoms can only absorb or emit light when they're in this gaseous low density form that corresponds to an energy level gap between the atoms. So what do we need to be able to, or what have we got written here? When an electron makes a transition from a higher to a lower energy level in an atom, the energy of the atom decreases and is released as a photon. That's what I was showing you here. The energy of the emitted photon is given by En minus Em equals Hf, where En minus Em is the energy difference of the atom, Hf is the energy of the photon, and F is the frequency of the emitted light. Basically, En, Em are the difference between the energy level it starts in and the energy level it finishes in. So here we could go, well, the energy difference here is equal to 13.6 minus 3.39. So that's equal to 10.21 electron volts. And let's just work across the bottom here. If we convert that to joules, 10.21 times 1.6 times 10 to the minus 19 will give us, let me just check here, 1.63 times 10 to the minus 18 joules. Then, so we know the energy, we can convert that to a frequency because we know that, let's actually change colours here. We know that E equals HF, so that F is equal to E on H, which is equal to 1.63 times 10 to the minus 18 divided by 6.63 times 10 to the minus 34, and that will give us a frequency of 2.46 times 10 to the 15 hertz. And then we can, hopefully I don't run out of room here, we can go C, the speed of light, equals F times wavelength. So the wavelength is equal to C on F. So that's equal to 3 times 10 to the 8th divided by the frequency, which was 2.46 times 10 to the 15 hertz. And that is equal to 1.22 times 10 to the minus 7 meters. And if we times that by a billion, that'll convert it to nanometers. There's a billion nanometers in a meter. So that comes out to be 121 nanometers would be the wavelength of that light due to that emission between those two energy levels. So that just is typical of the sort of questions that you would need to do. So hopefully now you can explain the presence of the discrete frequencies in line emission spectrum. You can solve problems involving emitted photons and electron energy levels of atoms, just like what I did there. You can draw energy level diagrams to represent the energies of different states in an atom. That's our energy level diagram here. Given an electron energy diagram, calculate the frequencies and wavelengths of the lines corresponding to specified transitions. Well, that's again just what we did at the bottom. Actually, that one probably applies to what we did at the bottom. This one here just applies to working out the difference in electron volts of the energy gaps. So that's just working out the energy. This is working out the frequency and the wavelength. And this one relates to drawing transitions on these energy level diagrams. So hopefully that is clear. So the only real atom we need to really know in any detail is hydrogen. And the energy level diagram I have been using so far in these slides is the energy level diagram for hydrogen. Now, what you need to be able to do, and this is quite straightforward, is draw on an electron energy level diagram of hydrogen, on this diagram here, transitions corresponding to each of the series terminating at the lowest 3 energy levels. So what are those 3 series? Well, firstly, there's the series that goes down to the ground level. So you could excite hydrogen into any of these energy levels here, and it will relax down into the ground level series here. The second one is the ones that go down to the first excited state, or on this diagram that's shown as the n equals 2. So that would be transitions going down to the first excited state, or the n equals 2 level. And the next one that you need to be able to do is I'll find the right coloured pen, down to the second excited state, or the n equals 3 level, which would be like those transitions there. So I think that's pretty straightforward, although sometimes it's so simple it seems confusing. But there is some more important thing we need to know about that. These transitions that come down to the ground level, like the one we just worked out, the 121 nanometers, that's a very short wavelength. It's shorter than visible light. These are in the UV region of the spectrum. If we go and calculate those energy levels and then work out the wavelengths, we will work out they're in the UV region of the spectrum. The ones to the n equals 2 are in the visible. They are the ones that we can see with our naked eye. And the ones that go to the n equals 3 are in the infrared region of the spectrum. So you need to either be able to work out, or just remember might be easier in this case, that transitions that go to the n equals 3 level are in the infrared, to the n equals 2 level are in the visible, and to the n equals the ground state are in the UV region. These have special names. They're called like the Passion, the Lyman, and the Balmer series. You don't need to remember which is which. I don't remember which is which, to be honest. But you may come across that in the book, or you may see it mentioned in a question, but you won't need to remember which is which. It'll be explicit which one they're talking about from the way the question is structured. So yeah, that is the line emission spectrum of hydrogen and those characteristic lines. So you should be able to draw the transitions and then relate them basically high energy, short wavelength, or high energy, high frequency, short wavelength, moderate energy, moderate wavelength, moderate frequency, low energy, low frequency, high wavelength. The second thing we need to know about is, or the final thing we need to know about for this subtopic, is ionisation energy. So the ionisation energy of an atom or an element, maybe I should be using again there, is the minimum energy required to remove a single electron from the atom in its ground state. So if we have a hydrogen atom here and it's in its ground state down here, what is the minimum amount of energy we need to put in to completely boot that right out of the electron? Right out of the atom. So think about all our metals, lithium, sodium, all reacting to lose an electron. What is the minimum energy we need with those when we're trying to get, full and empty outer shells in chemistry, if you remember doing that in earlier years? What's the minimum amount of energy we need to put in? And from this diagram, in this case here, the ionisation energy would be 13.6 electron volts. If we put in less than 13.6 electron volts, we would get it up to maybe one of these other stages, but it won't have enough energy to completely separate from the proton and leave the atom. The minimum we would need to put in is 13.6 electron volts. If we put in more than 13.6 electron volts, it's almost like the photoelectric effect again. That will cause that atom to be released, and basically the electron will have the remaining kinetic energy. So if we put in 14.6 electron volts, that could shoot an electron all the way out of the atom, and that atom could then leave with 1 electron volt worth of energy. So what do you need to be able to do? Using an energy level diagram, determine the ionisation energy in either joules or electron volts of hydrogen. Obviously, if we need to convert that to joules, we just times it by 1.6 times 10 to the minus 19. Should hopefully all be able to convert between joules and electron volts by this stage of your physics learning. That's it for this flip lesson. We'll continue looking at the structure of the atom in the next flip lesson.